One star drifts roughly 200 light-years away from our planet. You can locate it using binoculars on any clear evening. Researchers have calculated its age through satellites, orbital telescopes, and acoustic waves reverberating through its interior. Every time they do, the figure that returns is greater than the age of the cosmos itself. We are going to trace that inquiry from its origin, through every device that tried to crack it, through the revelations that deepened the mystery, and through the fracture line now splitting the core of contemporary cosmology. If you want to follow along as this unfolds, subscribe and ring the notification bell so you catch everything as it drops. The star has been burning for 14 billion years. It can wait. We probably cannot. Locate Libra on a clear evening. Raise binoculars and you are staring at one of the most unsettling objects in current science. The star sits somewhere between 190 and 201 light-years from Earth. Near enough to identify with basic optics, far enough that its light departed long before the American Civil War began. Catalog designation H, D 142283. Surface temperature around 10,040 degrees Fahrenheit, verified. These figures are not in dispute. The star exists. That part is straightforward. What follows is not. Every rigorous effort to determine the age of this object has yielded a value that should not be possible. Age projections have spanned 12 billion to 16 billion years, depending on the instruments, models, and era involved. The universe itself is verified to be 13.7877 billion years old, clocked by the Planck satellite in 2018. A star cannot predate the space in which it formed. The laws of physics prohibit it, and yet the readings keep arriving as contradictions, or something is broken, or everything is. Lift those binoculars once more. The star is not drifting gently. At roughly 800,000 miles per hour, it tears through space at a velocity that sets it immediately apart from the typical stars in this slice of the sky. Most nearby stars travel at speeds measured in the tens of thousands of miles per hour. This object belongs to another tier entirely. To make it concrete, if you could match its pace, you would traverse the full breadth of Earth's orbit around the Sun in approximately 11 minutes. Speed like that carries a message. It signals that the object originated somewhere atypical, covered an enormous distance, and has been in motion for an exceptionally long time. Astronomers first detected something unusual in 1912. Walter Sidney Adams, stationed at Mount Wilson Observatory, catalogued the star and logged its unusual drift across the celestial background. The technical term is high proper motion, meaning it migrates against distant stars at a rate that outpaces its neighbors. Adams recorded the observation and continued. He was assembling a catalog, not triggering an alarm. But the marker he left in 1912 would be retrieved again and again across the following 100 years, each retrieval pulling researchers further into a puzzle none of them could untangle. The star registers at magnitude 7.2, a hair below naked eye detection, which cuts off around magnitude 6. With any binoculars at all under reasonably dark skies, you can put this target in your field. There is something pointed about that. Most of the paradoxes in cosmology inhabit distances so remote and scales so vast that they exist only as mathematics. This one lives in Libra, reachable, pinned in space by coordinates any amateur can key into a phone app. The question it poses is not trivial. If this star genuinely predates the universe, then either the universe's measured age is wrong, or the dating methods contain a flaw, or the theoretical frameworks linking distance to age are missing something foundational. These are not fringe ideas. Each position has been advanced seriously by credentialed scientists in peer-reviewed literature. The inquiry launched in earnest long ago and has never fully closed. What sustains it is a measurement problem. Distance, chemistry, physics, and time all feed into one equation. Adjust any input and the result shifts. The question was never whether the star exists. The question is what it means that it does. 13.787 billion years. That figure represents verified science. The age of the universe drawn from the Planck satellite's analysis of the cosmic microwave background, released in 2018. It stands as the single best number humanity has produced for the age of everything. The measurement holds an uncertainty of roughly 20 million years in either direction, which sounds enormous until you consider the total is nearly 14 billion. In cosmological terms, it is tight. Now weigh what astronomers recovered when they tried to date this star. 16 billion years. That was the first serious figure to emerge from an era when the best distance reading came from the Hipparcos satellite. The technique applied was isochrone fitting. Think of it as reading a birthday from a portrait. Given a star's brightness, temperature, and chemical composition, theoretical models can reconstruct which stage it has reached along its evolutionary course, and, from that, how long it has been burning. The method is well established. The inputs are where complexity enters. 16 billion years sits 2 billion years above the universe's own age. Under standard cosmology, that is forbidden. Later, analyses revised the figure downward. 14.46 billion years plus or minus 0.8, then 13.8 billion plus or minus 0.5, then 14.2 billion plus or minus 0.4. Every revision reflected better instrumentation or corrected modeling. Every revision moved the number closer to the universe's boundary without landing cleanly below it. The error bars in certain estimates still intrude past that boundary in the wrong direction. Isochrone fitting merits closer examination because it depends so fundamentally on distance. The technique compares a star's observed brightness to the brightness that models forecast for stars of matching temperature and composition. If the distance is wrong, the actual brightness is wrong, and the age inferred from it is wrong. This is not conjecture. This is the foundational geometry of the method, validated through decades of stellar physics. A star's derived age behaves like compound interest on a miscalculated principle. A modest distance error at the start of the calculation blossoms into a billion-year error by the end, which raises the core question the field has grappled with across decades. Which number is wrong? First possibility. The star's age estimate carries an error in the distance, the chemical composition model, or the stellar evolution theory. Second possibility. The universe's age is wrong, meaning the expansion rate was miscalculated. Third possibility. Both measurements are accurate, and the frameworks connecting them omit something fundamental about how stars originate and evolve. All three options have substantial scientific backing. All three remain in some form unresolved. For anyone watching this tonight, that matters. Cosmology is the science of origins. It tells us when the universe began, how it transformed, and what the laws of physics resembled in its infancy. If a single well-documented star can destabilize that structure, then the structure is not as solid as textbooks imply. Scientists are aware of this. The debates exist in published literature, not concealed in laboratories. The star keeps returning ages that press against the boundary. Each revision shifts the number, but the gap never fully seals. The next question is whether the oldest estimate, the one that opened the crisis, was founded on error. It was. In 1989, the European Space Agency launched a satellite called Hipparcos, named after the ancient Greek astronomer. Its mission was geometric: capture the minute apparent shift in position that nearby stars exhibit as Earth moves around the Sun. That shift is called parallax, and it remains the most direct tool humans have for measuring stellar distances. Hipparcos surveyed 118,000 stars across its operational life, logging their positions to a precision of roughly 1 milliarc second. For scale, 1 milliarc second is approximately the angular size of a coin seen from 3,000 meters away. That precision was cutting edge in 1989. It was also insufficient. Applied to this specific star, the Hipparcos parallax produced a distance that, when run through isochrone fitting models, yielded an age of 16 billion years. The figure spread across the literature. Papers cited it. The crisis intensified. Through the 1990s and into the early 2000s, the star was treated as a genuinely impossible object, a data point poised to overturn established cosmology. Then Howard Bond began looking more carefully. Bond, working between the Space Telescope Science Institute and Penn State University, suspected the Hipparcos parallax for this star lacked the precision needed to underpin a reliable age. Starting in 2003, Bond and his collaborator Edmund P. Nalan, an instrumentation specialist at the Space Telescope Science Institute, launched a dedicated campaign using the Hubble Space Telescope's fine guidance sensors. These devices were not originally designed for stellar parallax work. They were engineering systems built to anchor Hubble onto reference stars during observations. Repurposed for precision astrometry, they became something far more capable. The campaign ran for 8 years. 11 separate observation epochs distributed across the full arc of Earth's orbit to capture the maximum parallax signal. The result, published in February 2013, was a parallax of 17.15 milliarc seconds, plus or minus 0.14. A 5-fold precision improvement over Hipparcos. For a star at this distance, that translates directly into a 5-fold improvement in distance accuracy. The corrected distance differed modestly from the Hipparcos value, but the downstream impact on age was substantial. The estimated age collapsed from 16 billion years to 14.46 billion years, plus or minus 0.8. Science had been wrong. Confirmed. The 16 billion year figure that circulated for more than a decade as evidence of a cosmological breakdown was, at its foundation, an instrument limitation. Hipparcos was the finest available tool at the time, and it was not adequate for this measurement. Bond's 8-year campaign produced precision the earlier satellite could never have matched. That does not settle the matter. 14.46 billion years still exceeds the confirmed universe age of 13.787 billion years. The error bars on Bond's result allow the true age to fall below the universe's boundary, but they equally permit it to remain above. The crisis shrank. It did not vanish. What Bond's work established is that the most extreme historical estimates were artifacts of poor instrumentation. That insight cuts both ways. First, it means some of the drama around this star arose from imprecise data. Second, it means the remaining gap, the one that persists through all available improvements, represents genuine data demanding a genuine explanation. 800,000 miles per hour. Sit with that number. Earth orbits the Sun at roughly 67,000 miles per hour. The fastest spacecraft ever launched by humanity, the Parker Solar Probe, reached around 430,000 miles per hour at its closest solar approach. This star moves at twice that speed relative to the average motion of nearby stars. Velocity on that scale does not belong to an ordinary Milky Way resident. When astronomers reconstruct the star's path through the galaxy, tracing backward through confirmed proper motion and radial velocity data, the orbit does not resemble that of a star born inside the Milky Way's disk. It traces a highly elongated path, a wide ellipse that swings deep into the galactic halo and arcs back. Stars following trajectories like that are called halo stars. Most halo stars did not originate in the Milky Way. They arrived from outside. The leading explanation, confirmed to the extent that orbital mechanics allows, is that this star was born inside a small dwarf galaxy, a satellite of the early Milky Way. More than 12 billion years ago, that dwarf galaxy was consumed. Tidal forces shredded it. Its stars scattered into the halo, preserving the velocity they carried before the merger. This star is one of those remnants. The originating galaxy has never been pinpointed. It was absorbed before humanity existed, before the Earth coalesced, before our Sun ignited. The record of what that galaxy was, its geometry, its mass, its composition, was erased by the very merger astronomers are trying to reverse engineer. What survives is the velocity and the orbital profile it implies. This recontextualizes the star significantly. When astronomers first flagged it as unusual, the working assumption was that it belonged to the Milky Way, either a very old disk resident or a locally formed halo star. The velocity data dismantled that picture. The object preserves the memory of a galaxy that no longer exists, encoded in the direction and magnitude of its motion. It is a physical relic from an era before the Milky Way assumed its present form. The implications stretch beyond this single object. If the star formed in the early cosmos inside a galaxy that predated the Milky Way, its age is not just a number on a chart. It is a physical boundary on when the first stars could have formed following the Big Bang. The universe, as confirmed by Planck in 2018, is 13.787 billion years old. A star that crystallized inside a galaxy old enough to merge with the proto-Milky Way more than 12 billion years ago must have formed in the universe's earliest epoch, within its first 1 to 2 billion years. That leaves almost no gap between the Big Bang and this star's birth. Minimal gap means minimal tolerance for error. And tight tolerances mean that any inaccuracy in the age estimate, any defect in the models, any drift in the distance calibration does not affect only this star. It affects the entire picture of how the universe progressed from undifferentiated space to structured galaxies. The star holds more history than its light implies. In the early universe, iron did not exist. That sentence is simple. Its implications take time to absorb. The Big Bang generated hydrogen, helium, and faint traces of lithium. Every heavier element, everything that populates the periodic table beyond those three, was manufactured inside stars. Carbon, oxygen, calcium, iron, all requiring the nuclear furnaces of stellar interiors, and in many instances the violent deaths of those furnaces in supernova explosions that broadcast newly forged elements into the surrounding gas. new stars then crystallized from that chemically enriched debris. Each generation passed a heavier chemical inheritance to the next. Iron is a late product. It requires several stellar generations to accumulate in any meaningful concentration. A star born in the early universe, before those generations had cycled through, would carry virtually no iron whatsoever. When astronomers Joseph Chamberlain and Lawrence Aller analyzed this star's spectrum in the early 1950s, they measured iron at roughly 1/250th of the concentration found in our Sun. The technical notation is Fe/H, the iron-to-hydrogen ratio on a logarithmic scale. The confirmed value sits near -2.4. On a scale where 0 represents the Sun and -1 means 10 times less iron, -2.4 represents approximately 250 times less iron. The star is chemically stripped to a degree that speaks directly to its antiquity. This is confirmed spectroscopy replicated across decades of work. The classification arising from that figure is population 2. Astronomers categorize stars by metallicity, the catch-all label for everything heavier than hydrogen and helium. Population 1 stars are metal-rich, formed recently on galactic timescales, nested in spiral arms where enriched gas collects. Population 2 stars are metal-poor, born early, found in globular clusters and the galactic halo. Population 3 stars, never directly observed, are theorized to be the primordial generation, assembled from pure Big Bang matter with essentially zero metals. This star falls firmly in population 2. Confirmed. The iron abundance functions as a timepiece differently than stellar evolution models do. Evolution models track how a star transforms over time as it consumes fuel. Metallicity tracks which epoch of cosmic history generated sufficient iron for stars like this to form in the first place. Both approaches agree. The star emerged early. Very early. Here is the specific boundary metallicity imposes. For a star to carry an iron-to-hydrogen ratio of -2.4, it had to form before many generations of stars had already run their course. Rewinding the stellar enrichment models, the established timeline places formation within the universe's first 2 billion years. Some estimates push it into the first billion. The oxygen abundance provides an independent check. The confirmed oxygen-to-hydrogen ratio sits near -1.67. A shift of just 0.15 in that ratio displaces the inferred age by 0.7 billion years. The star's chemical fingerprint is sensitive enough that modest measurement errors cascade into large age discrepancies. This is precisely why multiple independent lines of evidence matter. The chemistry confirms age. What it cannot determine alone is precisely how much age. For that, distance is required, and the distance, as already established, was incorrect for a long time. Even corrected, the problem refused to disappear. It only contracted. On the southern slope of the San Gabriel Mountains, roughly 28 miles northeast of Los Angeles, the 60-inch telescope at Mount Wilson Observatory was the largest working instrument in the world in 1912. Its mirror, polished to specification in Paris and shipped by sea to California, granted astronomers a clarity of stellar detail that no earlier tool could match. The mountain's elevation, approximately 5,700 feet above sea level, placed observers above much of the atmospheric moisture that blurs ground-based observation near the coast. Walter Sidney Adams worked there during a productive chapter in the observatory's history. A meticulous recorder, He was constructing systematic logs of stellar spectra and positions at a time when the field was still charting the sky's basic inventory. In 1912, he logged the star later catalogued as HD 142283. He noted something particular about its behavior. The star moved. Proper motion is the apparent drift of a star against the fixed backdrop of more remote stars, measured across months and years of systematic observation. Most nearby stars show measurable proper motion, but the rate varies substantially depending on actual velocity and distance. This object moved at a rate that stood apart. Adams recorded it as a high proper motion star, consistent with the exceptional velocity that would eventually be measured more precisely at roughly 800,000 miles per hour relative to the local standard of rest. He was not raising a cosmological alarm. He was recording an anomaly in a catalog entry. The significance of that motion would take generations to fully unfold. The arc originating in 1912 is worth holding in mind. A catalog flag becomes a spectroscopic analysis, which becomes a parallax crisis, which becomes a cosmological debate. Every investigator who followed Adams believed they were solving a bounded problem. Each one found the problem was larger than the version they inherited. 1912 is also worth marking for another reason. The tools Adams deployed at Mount Wilson were precise by their era's standards, but lacked the capabilities that mattered most for age determination. Chemical composition at the sensitivity required to detect iron depletion, and parallax at the precision required to nail down distance. Those capabilities came later. Chamberlain and Ahler's spectroscopic work in the early 1950s identified the iron deficit. The Hipparcos satellite in the 1990s attempted the parallax. The Hubble Fine Guidance Sensor campaign ran from 2003 to 2011. Each instrument generation answered part of the question and opened new uncertainty. Consider how 1912 appeared through a cosmological lens. The concept of an expanding universe did not yet exist. Many astronomers still believed the Milky Way constituted the entire cosmos. Dark matter was untouched by theory. The Big Bang had not been proposed. The framework that would eventually render this star's age anomalous simply had not been constructed. Adams logged it into a universe that did not yet know how old it was. Over the 111 years that followed, the field assembled that knowledge carefully, measurement by measurement. The more precisely it measured, the more clearly this specific object resisted simple classification. The star Adams entered into a catalog in 1912 became the star that kept shattering every timekeeping method scientists aimed at it. Stellar evolution models rest on physics that is, in most respects, confirmed to high precision. The core processes, hydrogen fusion, energy transport, pressure balance, are well characterized. A model is only as reliable as its assumptions, however. And, for most of the 20th century, those models carried an assumption that turned out to be wrong in a specific and consequential way. The assumption was that stellar interiors are chemically well mixed. Take a star and, within the model, distribute its chemical elements uniformly throughout its volume. Hydrogen and helium blended evenly from core to surface. The simplification made calculations tractable before computers could handle the full physical complexity. For many applications, it was serviceable enough. For dating old metal-poor stars, it introduced a systematic error that inflated ages by roughly 1 billion years. The physical process the models omitted is called atomic diffusion. Gravity inside a star does not treat all atoms equivalently. Heavier elements, including helium, experience a stronger net downward pull relative to their buoyancy in the surrounding plasma. Over billions of years, this drives heavier elements gradually toward the core, while lighter hydrogen migrates upward. The process unfolds imperceptibly slowly. On human timescales, or even geological ones, it is invisible. Over billions of years, it restructures the chemical layering of the stellar interior in ways that alter how the star appears from outside. A star that has experienced significant helium diffusion registers from its surface brightness and temperature as slightly different from what well-mixed models predict. Models interpreting that surface profile will infer the star is older than it truly is. The bias is systematic. It affects every aged metal-poor star, analyzed with models that exclude diffusion. For most of the 20th century, the Heights models excluded it. Don A. Vandenberg, a researcher at the University of Victoria in Canada, developed what became known as the Victoria-Regina stellar evolution models, incorporating atomic diffusion as a full physical process rather than treating it as negligible. The effort was part of a broader push in stellar astrophysics to identify and eliminate systematic biases in age estimates applied to ancient metal-poor stars of exactly the type represented here. The correction was substantial, approximately 1 billion years. Science had been wrong, confirmed. Models excluding diffusion had systematically overstated ages. When Vandenberg's revised models were applied to this star, the inferred age fell by roughly 1 billion years. A billion-year correction sounds large because it is large. It is also a correction that addresses a physical process that was happening inside the star the entire time. Whether or not the models acknowledged it, the helium was always sinking. The models simply failed to account for it. Combine the distance correction from Bond's parallax campaign, which moved the age from 16 billion down to 14.46 billion years, with the diffusion correction from improved stellar models, and the age continues tracking toward the boundary. The gap between star and universe narrows but does not close. 1 billion years recovered from better models, another 1.5 billion from a better distance. The universe's confirmed boundary stands at 13.787 billion years. Even with every correction applied through 2013, the star's age still hovered near 14 billion. The residual gap kept researchers searching for the next thing science had gotten wrong. Another correction was coming. By 1993, the problem had grown conspicuous enough to appear not in a specialized astrophysics publication, but in Science, one of the most widely read research journals on Earth. The article was not framed as a curiosity or minor inconsistency. The field was acknowledging an open emergency. Stars in globular clusters, specifically M92 and M15, two of the oldest known clusters in the Milky Way's halo, were returning ages exceeding the calculated age of the universe by 1 billion years or more. This star was one point in a pattern spread across dozens of objects. Globular clusters are gravitationally bound assemblages of tens of thousands to millions of stars, all formed at roughly the same moment from the same gas reservoir. Because every star in a cluster shares a birth date, their collective properties provide a more robust age estimate than a single star can. The technique is called main sequence turn-off fitting. Stars above a threshold mass evolve away from the main sequence at a predictable rate. The point at which a cluster's stars begin peeling off that sequence marks how long the cluster has been burning. It is a validated and widely tested method. M92 and M15 both generated ages above the universe's calculated limit. The Science article framed this as a genuine emergency. Either stellar physics contained an error large enough to add 1 or more billion years to every old star's age estimate, or the universe's expansion rate had been miscalculated, meaning the universe was actually older than current models allowed. Both implications carried serious consequences. The first would demand a fundamental overhaul of stellar evolution theory. The second would require revising the cosmological model itself. Multiple independent teams deploying different instruments and different clusters reached the same conclusion. The oldest stars were too old for the cosmos they inhabited. The uniformity of the result across many distinct objects made it difficult to dismiss as a localized measurement artifact. When 10 different clocks all read the same wrong hour, the problem is most likely with the calendar, not the clocks. For this particular star, 1993 marks the moment the question shifted from whether this object was anomalous to what underlying physics it was pointing toward. That reframing matters. A single anomalous measurement can be set aside until better data arrives. A systematic pattern across the oldest structures in the observable universe is a different category of problem, one demanding a theoretical resolution rather than just improved instruments. The corrections that followed, better parallax work, refined stellar models, diffusion physics, all arrived after this public acknowledgement that something was genuinely broken. The crisis published in Science was not the start of the problem. Researchers had been aware of the tension for years, but appearing in a mainstream journal signals a threshold. The community has decided the discrepancy is real enough to argue about in the open. What followed was essentially a war. Two factions of cosmologists, each with substantial credibility and considerable data, had been clashing since the 1980s over a single number: how quickly the universe is expanding. That number fixes the universe's age. The two sides disagreed by a factor of 2. The resolution of that disagreement would determine whether the globular cluster emergency was real or an artifact of a miscalibrated universe. The Hubble constant describes the universe's expansion rate. Expressed in kilometers per second per megaparsec, it tells astronomers how rapidly 2 points in space diverge for every megaparsec of separation between them. 1 megaparsec equals roughly 3.26 million light-years. The Hubble constant sets the cosmic clock. Higher values imply faster expansion, meaning the universe reached its current size more quickly, meaning it is younger. Lower values imply slower expansion and an older universe. For most of the 1980s and 1990s, two camps in cosmology could not reconcile on this number. The disagreement was not a rounding error. Alan Sandage, among the most seasoned observational cosmologists of the 20th century, spent decades arguing for a value near 50 kilometers per second per megaparsec. At that rate, the universe's age comes out to roughly 20 billion years. If correct, there was no crisis. The oldest globular clusters and the oldest stars would sit comfortably inside a 20 billion year universe with generous room to spare. Gérard de Vaucouleurs held the opposing position. His measurements consistently returned values near 100 kilometers per second per megaparsec. At that rate, the universe is approximately 10 billion years old. Under that figure, the crisis was catastrophic. Metal-poor stars in globular clusters would be 40% older than the universe they inhabit. A factor of 2. Two credentialed researchers working with real data arriving at values differing by a factor of 2 on a single foundational number. The consequences for the star under study here were direct. Depending on which camp was right, the object was either a comfortable data point inside a well-aged universe or physical evidence of a rupture in cosmological theory. Conference discussions during that era are described by participants as fierce. Sandage and de Vaucouleurs were not diplomatic about the disagreement. Each accused the other's team of systematic measurement errors. Each had allies with their own data and analyses. The dispute came to be called informally the Hubble Wars, and it ran without resolution for roughly 2 decades. The Hubble Key Project, a major observational campaign designed specifically to settle the question, published its final answer in 2001. The result, approximately 72 kilometers per second per megaparsec, implying an age of roughly 13 to 14 billion years, nearer to Sandage's end than de Vaucouleurs', but short of either extreme. The Key Project did not fully settle the dispute because different measurement approaches kept returning slightly different values. This remains unresolved in a precise technical sense. The Planck satellite's measurement of the cosmic microwave background yields approximately 67.4. The value derived from direct local measurements using variable stars and supernovae sits near 73. The gap between them is 5 sigma, meaning it is statistically implausible as a random fluctuation. Something in one or both measurement chains carries a systematic error. Scientists call this the Hubble tension, and it stands as one of the deepest unresolved questions in cosmology. What the Hubble Wars clarified is that the universe's age was not settled. It was a contested figure, sensitive to method and instrument, capable of swinging the verdict on whether old stars violated physical law. The star in Libra was caught in the crossfire of a larger argument. The most careful age measurement it had ever received had not yet been attempted. That measurement was about to begin. In 2003, Howard Bond confronted a specific problem. The age estimates for this star depended critically on its distance. The distance depended on parallax. The best available parallax from the Hipparcos satellite had precision of roughly 1 millisecond. Bond had already determined that 1 milliarcsecond was not adequate to compress the age uncertainty below the critical threshold, separating the star's measured age from the universe's confirmed one. The parallax needed to be roughly 5 times sharper. The instrument capable of that was already orbiting the Earth. It just was not designed for this purpose. The Hubble Space Telescope's fine guidance sensors are, at their core, interferometric devices. Their intended function is to stabilize the telescope during observations by locking onto bright reference stars, holding Hubble's pointing to within a fraction of an arc-second. Lock on to 2 guide stars simultaneously, and the telescope holds steady. Steady enough to generate the exposures that produced the Hubble deep fields. Steady enough to resolve surface details on Pluto. The sensors were engineering infrastructure, pointing control equipment. They held the science instruments stable so that other researchers could conduct science. Bond and Edmund P. Nalin, N.H. Chiat, instrumentation specialist at the Space Telescope Science Institute, recognized that the same interferometric precision that made the sensors superb pointing tools also made them capable of astrometric measurements beyond what any ground-based instrument could achieve. With careful calibration and a sufficient baseline, the sensors could resolve stellar positions to fractions of a millisecond. The parallax of a star 190 to 201 light-years away becomes measurable at that precision in a way it simply is not at 1 millionth second. The campaign required patience. One observation is not enough. Parallax measurement requires observing the star at multiple positions in Earth's orbit and tracking how its position shifts against background stars. The shift is tiny, roughly the angular width of a human hair viewed from about 2 meters. Reliable measurement demands multiple epochs spanning multiple years. Sampling the full parallax ellipse the star traces as Earth orbits the Sun. Bond and Nalen ran 11 observation epochs across 8 years, from 2003 to 2011. 11 is a deliberate number. Each epoch contributes an independent position measurement. More epochs suppress statistical noise and expose systematic errors. For a measurement of this precision, pushing into territory no previous instrument had covered for this particular star, the team needed enough data to be certain the final parallax was real, and not an artifact of sensor drift, calibration irregularities, or geometric limitations from a short observation baseline. 8 years provided baseline depth. 11 epochs provided statistical robustness. Every observation required scheduling time on a telescope that hundreds of teams competed to use. Hubble is typically oversubscribed by a factor of 6 or 7. For every awarded hour of observing time, 6 or 7 proposals go unfunded. Sustaining an 8-year campaign across successive telescope allocation cycles meant the scientific case had to survive repeated scrutiny. In February 2013, Bond and Nalen published their measurement. The parallax, 17.15 millionth seconds, plus or minus 0.14, 5 times sharper than Hipparcos. The age derived from that distance was 14.46 billion years, plus or minus 0.8. The value that had anchored the crisis for 2 decades was an artifact of insufficient precision. But 14.46 was still not safely below the universe's boundary. The gap had narrowed. The problem had not closed, and the instruments needed to press the question further had not yet been turned toward this star. Oxygen does more than trace quietly through an aging star's interior. It plays a structural role. Oxygen shapes how efficiently a star's interior retains radiation, a property physicists call opacity. Picture opacity as fog between yourself and a signal beacon. Denser fog means the signal takes longer to reach you. Inside a star, higher oxygen content means radiation travels more slowly outward from the core. The star's energy, transport shifts. Its radius at any given age shifts. Because astronomers work backward from a star's present brightness to reconstruct its history, the calculated age shifts whenever the opacity shifts. This is confirmed physics. The relationship between oxygen content and stellar opacity appears in every major stellar evolution code in active use. What was not established for most of the 20th century was precisely how much that relationship mattered when dating one specific ancient star using imprecise chemical measurements. For decades, astronomers treated oxygen abundance as a secondary variable. They incorporated it into models, acknowledged it, and then assumed its contribution to the total age uncertainty was modest enough to absorb into the general error budget. That assumption proved wrong. Howard Bond's team worked through the complete uncertainty budget for their 2013 analysis, accounting for every physical variable capable of nudging the age estimate in either direction. When they arrived at oxygen, they found something that had been lurking in the arithmetic for years. Oxygen was the single largest remaining source of age uncertainty for this star. A change of just 0.15 decs in the oxygen-to-hydrogen ratio, the standard unit for measuring stellar chemistry on a logarithmic scale, shifts the inferred age by 0.7 billion years. 700 million years suspended on one number that the field had quietly treated as resolved. The star's oxygen-to-hydrogen ratio sits near minus 1.67. That value means its oxygen content is roughly 2% of what the Sun carries, consistent with formation in the very early universe before heavy elements had been widely forged and dispersed by dying stars. This value represents the current best estimate. Whether it is precise enough to resolve the age question remains open. Precision matters acutely here because the star is genuinely difficult to characterize. Formed before heavy elements were widespread, it carries almost no metals. Measuring oxygen requires analyzing extremely faint spectral absorption features, signals hovering at the threshold of instrumental resolution. Different research teams deploying different equipment have arrived at slightly different oxygen values. As of early 2026, no scientific consensus exists on the precise figure that most directly governs the final age. Consider what this implies alongside the age paradox. Bond's best estimate came to 14.46 billion years. The universe's confirmed age from the best available cosmological data runs approximately 13.8 billion years. The difference between those two numbers is roughly 0.6 billion years. The oxygen uncertainty alone can swing the age calculation by 0.7 billion years in either direction. One variable, sitting just outside the grasp of available precision instruments, determines whether this star falls inside the universe's timeline or shatters it. Science had treated oxygen as background noise. Bond's 2013 paper confirmed it was the loudest signal in the problem. The age of 14.46 was constructed on an oxygen value the community had never pinned down with sufficient precision to close the paradox. The paper landed in the Astrophysical Journal in February 2013. The title was measured. The methodology was thorough. The result? 14.46 plus or minus 0.8 billion years. The authors noted throughout that the error bars were shaped in part by the unresolved oxygen question and by uncertainties in how stellar models handled the gradual settling of helium toward the stellar core over billions of years. Press coverage arrived differently. Science journalism operates through compression. A paper with a 10-page methods section becomes a headline, a summary sentence, and a pull quote. Here, the compression yielded a clean narrative. The paradox of the oldest star had been resolved. The star's error bars technically permitted an age below the universe's. The problem was declared closed. Howard Bond was considerably more precise. The center of his probability distribution still sat at 14.46 billion years, a value that still exceeded the universe's estimated age at that time. His lower 1 sigma bound, the value 1 standard deviation below the best estimate, came to 13.66 billion years. 1 sigma means the true value has roughly a 16% chance of falling below that line. It also means an 84% chance of landing above it. A 16% chance of fitting inside the universe is not the same thing as fitting inside the universe. The oxygen uncertainty Bond flagged remained unresolved within the paper. The helium diffusion treatment in the stellar models remained uncertain. Both variables were capable of shifting the age by hundreds of millions of years. Neither received headline treatment. Consider an analogy. An athlete claims to have run a mile in 3 minutes and 50 seconds with a stated uncertainty of plus or minus 40 seconds. The world record stands at 3 minutes 58 seconds. The athlete's lower bound technically falls beneath the record. Does that break the record? The honest answer is that the performance is consistent with a record-level result, not proof of one. Bond published a measurement consistent with the star fitting inside the universe. The press received it as a resolved paradox. Scientific error bars carry probabilistic weight. The lower bound of Bond's range was produced by the same chain of uncertain inputs that generated the central estimate. Treating the lower bound as the answer meant implicitly selecting the most favorable reading of every uncertain variable simultaneously. That is not how probability distributions function. The gap between scientific nuance and public interpretation matters because it determines how problems get funded, pursued, and re-examined. When a question is declared resolved, momentum to keep measuring dissipates. If oxygen uncertainty is the controlling variable and it remains unsettled, the problem has not closed. The headline and the underlying data were pointing in opposite directions. 1 month after Bond's paper appeared, a different data set landed. It came from a satellite that had spent years staring at the oldest light in existence. Not at stars, but at the faint thermal remnant of the Big Bang itself. The number it produced would force a new accounting and would compress the margin between this star's lower error bound and the universe's confirmed age down to something uncomfortably thin. In March 2013, the European Space Agency released the first comprehensive results from the Planck mission. The Planck spacecraft had spent more than 2 years mapping the cosmic microwave background, the faint thermal radiation left over from the Big Bang, covering the entire sky with resolution surpassing any previous instrument. Planck did not study stars. It studied the cosmos as a whole, reading the fine-scale structure of ancient light to extract the universe's expansion rate, its composition, and its age. The confirmed result from the March 2013 data release, 13.82 billion years, more precise than any prior estimate, slightly higher than earlier best figures. Hold that number. Return to Bond's result. His best estimate was 14.46 billion years. The lower 1 sigma bound, the minimum age the data could reasonably support, was 13.66 billion years. The gap between Bond's lower bound and the Planck universe age, 13.82 minus 13.66. That arithmetic yields 0.16 billion years, 160 million years. That figure sounds enormous by any human measure. On the scale of the universe, it is less than 1.2% of the total age. To put it as a spatial analogy, if the universe's age were a highway stretching 100 miles from coast to coast, the margin separating this star from the boundary would be approximately 1 mile and a quarter. The question raised by that margin remains open. Does it represent genuine resolution, or a near miss that future measurements will snap back open? The Planck 2013 result carried its own uncertainty range. The Bond result carried its oxygen uncertainty. When 2 measurements each carry their own error, apparent agreement at their outer boundaries does not dissolve the underlying tension. It compresses it into a narrower space. Planck published a final, more refined age in 2018, 13.787 billion years, slightly lower than the 2013 number. That small movement shifted the universe's confirmed age fractionally closer to Bond's lower bound rather than away from it. The margin contracted further. Both outcomes remained viable in the data as of early 2026. A shift of just 0.16 billion years in either direction would alter the picture entirely. If a future revision raised the universe's age slightly, Bond's lower bound would drop further below it. If a refined oxygen value pushed the stellar age downward by the same increment, the paradox would dissolve. The outcome was suspended over the smallest gap either measurement could conceivably traverse. For this star to fit cleanly inside the universe's timeline, its age estimate needed to fall, its oxygen value needed to shift more favorably, its distance needed to hold, or the stellar models needed refinement. For the paradox to worsen, any single variable needed to push the other way. The question was never whether the numbers could be made to touch at their margins. The question was whether the center of the age distribution could be brought below the confirmed universe age without relying on contested inputs. That question remained open, and the tools available to press it carried their own unresolved complications. Complications that had been quietly accumulating since before Bond had written a single sentence of his paper. Before Bond published his 2013 analysis, before the next generation of instruments had been trained on this star, a warning had already appeared. It came from a cluster of stars so familiar that human civilizations across the globe and across millennia had given them names. The Pleiades cluster sits roughly 440 light-years from Earth. 7 stars are visible without optical aid on a clear night. Hundreds more populate the surrounding field through a telescope. Astronomers have examined this cluster with every major instrument built across the past century, making it among the most thoroughly characterized groups in the sky. Before the Hipparcos satellite launched, distance estimates to the Pleiades from multiple independent approaches, including spectroscopic parallax and main sequence fitting, had converged within a consistent range. Then Hipparcos measured it. The same instrument that generated the distance used in Bond's age calculation placed the Pleiades at roughly 120 light-years. Independent estimates from ground-based techniques and main sequence fitting consistently place the cluster at around 135 to 140 light-years. The discrepancy was approximately 10%. No clean explanation for that gap ever emerged within Hipparcos's formal error model. This is confirmed. The satellite's stated uncertainties did not account for the deviation. A systematic bias was present in that measurement. Its origin remained, and in some respects still remains, a subject of technical debate among astrometry specialists. The significance of that systematic deserves careful attention. Hipparcos represented the finest satellite astrometry of its era. Its results had been cited across thousands of research publications. If systematic errors affected the Pleiades at 10%, then every individual distance in the catalog carried an unquantified additional uncertainty layered on top of the formal error bars. Here is why this matters for the star at the center of this investigation. The distance Bond's team used, derived from Hipparcos data, fed directly into the luminosity calculation. Luminosity fed directly into isochrone fitting. Isochrone fitting produced the age. Every step in that chain depended on the Hipparcos distance being reliable at the level the age paradox demanded. If Hipparcos was off by 10% on the Pleiades, one of the most thoroughly studied clusters in the entire sky, then individual stellar measurements from that catalog offered no guarantee of comparable precision for nearby halo stars or for the specific object at the heart of this inquiry. Science had treated Hipparcos as the authoritative astrometric standard for precision distance work on nearby stars. The Pleiades result showed that the catalog was dependable in aggregate, but carried real systematic risk at the individual measurement level. For an age paradox measured in increments of hundreds of millions of years, that level of systematic risk was enough to keep doubt alive. The warning from the Pleiades did not deter Bond from using the Hipparcos distance. There was no superior option. The next generation instrument capable of superseding it had been funded and designed but had not yet launched. What the Pleiades result had established, clearly and without resolution, was that any age founded on Hipparcos data should be treated as provisional until a more precise instrument confirmed or revised it. That more precise measurement was coming. It had been built, tested, and launched. The question was what it would find. The technique converting raw observations into stellar ages deserves a closer look. The tool is called an isochrone. Understanding why it matters requires briefly picturing what it actually is. An isochrone is a theoretical curve. It represents all the stars sharing the same age while spanning a range of different masses. Trace a curve through the positions on a temperature-brightness diagram where you would expect to find 10-billion-year-old stars of varying sizes, and you have a 10-billion-year isochrone. Fit an observed star onto that grid, and you can read off its approximate age from where it falls relative to the curves. The technique works because a star's position on that diagram shifts predictably as it ages and consumes its hydrogen. The word theoretical in that description carries weight. An isochrone is only as accurate as the physical inputs used to construct it. It encodes assumptions about how stars move energy, how helium settles toward the core across billions of years, how opacity responds to varying temperatures, and how nuclear reactions proceed under extreme pressure. Alter any assumption and the isochrone shifts position. Shift the isochrone, and the age derived from fitting an observed star shifts with it. 3 major isochrone suites exist for work of this kind. Don A. Vandenberg at the University of Victoria developed the Victoria-Regina models, used extensively for metal-poor halo stars. The Parsec suite was assembled by a team based primarily in Padova. The Basti suite originated at the Teramo Astronomical Observatory. Each of these model families uses slightly different physical inputs, slightly different treatments of interior convection, and slightly different opacity tables. All 3 are produced by skilled scientists using the best physics available. Applied to the same observational data, they do not return the same age. When researchers supplied Gaia data release, 3 photometry and parallax to the Parsec and Basti suites, they arrived at 13.8 plus or minus 0.5 billion years. When a different team applied the modules and experiments in stellar astrophysics code, combined with direct diameter measurements from the Cara array in 2021, they arrived at 12 plus or minus 0.5 billion years. The underlying distance data for both analyses came from the same satellite. The resulting ages differed by nearly 2 billion years. The model is the measurement. That statement sounds alarming, and it should. When an observation is processed through a theoretical framework before it becomes a number, the resulting number carries the framework's assumptions as fully as it carries the star's actual signal. Observers cannot step outside those assumptions. Every age yielded by isochrone fitting reflects the physics embedded in the model as much as it reflects the light arriving at the detector. Stellar ages are conditional. The age of 14.46 billion years is the age assuming Bond's chosen physical inputs. The age of 12 billion years is the age assuming a different and arguably more direct set of constraints. Both are legitimate results. Both were produced rigorously. What they cannot both be simultaneously is precise, and the gap separating them was about to encounter a discovery that had already, once before, shifted the entire calculation of the universe's age by more than 1 billion years. Return to 1993 for a moment. Astronomers were measuring the ages of the oldest globular clusters in the galaxy, dense concentrations containing hundreds of thousands of ancient stars. Results were converging on ages between 15 and 17 billion years. The problem was that the universe itself, based on the expansion rate then measured, appeared to be somewhere between 8 and 12 billion years old. Stars older than the universe. The same paradox wearing a different face, and the answer that dissolved it did not come from improved stellar measurements. In 1998, two independent research teams were examining distant supernovae. Saul Perlmutter led the Supernova Cosmology Project. Brian P. Schmidt and Adam Rees led the High Z Supernova Search Team. Both groups were measuring Type 1a supernovae, a category of stellar explosion that reaches a predictable peak luminosity. Because the peak is known, observing how bright the explosion appears in the sky tells you how far away it is. Astronomers call them standard candles, calibrated reference markers for cosmic distances. The supernovae in the most remote galaxies were dimmer than expected. Dimmer meant farther. Farther at those distances meant the universe's expansion had been accelerating over time rather than decelerating. A decelerating universe, the standard assumption through most of the 20th century, would have placed those distant explosions closer. The data placed them farther. Acceleration required a previously discarded ingredient, a cosmological constant, a term Einstein had added and then removed from his field equations, representing energy intrinsic to empty space. Researchers called it dark energy. Its fundamental nature remains unknown. What was confirmed in 1998 and has remained confirmed ever since is that the universe's expansion is accelerating. That single finding shifted the universe's calculated age by more than 1 billion years. A decelerating universe expands rapidly early and slows later, implying a shorter elapsed time for a given expansion rate. An accelerating universe has an entirely different age geometry. The recalculated age, with dark energy incorporated into the equations, pushed the universe older than it had previously seemed. The globular cluster crisis that had persisted since 1993 largely dissolved. Saul Perlmutter, Brian P. Schmidt, and Adam Rees shared the Nobel Prize in Physics in 2011 for their role in what became one of the most consequential revisions in the history of cosmological science. The speed with which that revision was accepted said something important about the quality of the evidence. Two entirely independent teams had arrived at the same conclusion from independent data sets and independent analytical methods. That independent confirmation moved what had initially appeared to be an instrument problem into the domain of a genuine physical discovery about the nature of the universe itself. This precedent hangs over every conversation about the current paradox. The universe's age is a derived quantity. It emerges from a model, and that model has been radically revised before within living scientific memory. The confidence with which the current figure of 13.787 billion years is stated reflects the quality of current data and models. It does not guarantee that number will survive the next major revision. The paradox once dissolved when the framework changed rather than when the stars were remeasured. Whether that could happen again became the most pressing question in the entire investigation. The European Space Agency launched Gaia in December 2013, a spacecraft designed to do one thing at a scale never before attempted: measure the positions, distances, and motions of more than 1 billion stars with extraordinary precision. Where Hipparchos had catalogued roughly 100,000 stars and achieved a precision of about 1 millisecond, Gaia aimed for precision 10 to 100 times finer across a catalog 1,000 times larger. Keeping the spacecraft thermally stable while it rotated continuously was an engineering requirement that defined the 5-year primary mission. 2 telescopes aboard the craft observed the sky simultaneously at different angles, allowing its computers to build a self-consistent geometric model of stellar positions without depending on any pre-existing reference frame. Every star it measured helped constrain the positions of every other star it measured. For the star at the center of this investigation, Gaia's first relevant result appeared in the early data release 3 published in December 2020. A refined parallax replaced the Hipparchos value that had anchored Bond's 2013 analysis. Researchers had been waiting for this measurement for years. The Gaia parallax placed the star at approximately 201 light-years. That figure, confirmed in the full data release 3 published in June 2022, was consistent with Bond's Hipparchos-based estimate, but substantially more precise. The systematic risk that had haunted every Hipparchos-derived stellar distance since the Pleiades discrepancy was not fully eliminated from the field, but for this star specifically, the Gaia measurement provided a far more reliable foundation than anything available before. Feed the Gaia distance into isochrone models, and the age calculation runs again with a more secure anchor at the base. Using the Parsec and Basti suites, the result came to 13 to 14 billion years. The central value, 13.8 plus or minus 0.5 billion years, lands essentially at the boundary of the universe's confirmed age. That outcome, which sounds like progress, actually sharpens the paradox rather than resolving it. Bond's 2013 error bars were wider, allowing more statistical room for the age estimate to drift below the universe's timeline. The Gaia-based result tightened those bars considerably. With less room to shift downward, the paradox became more precisely characterized. The star was no longer ambiguously old. It was precisely positioned at the exact boundary where the contradiction lived. 13.8 plus or minus 0.5 billion years. The universe's age, 13.787 billion years. The center of the distribution sits above the confirmed age. The upper bound reaches to 14.3 billion years. The lower bound at 13.3 falls comfortably below. The star remained statistically consistent with fitting inside the universe, but with a central estimate that still exceeded it. Gaia had not eliminated the problem. It had confirmed the problem was real, precisely measured, and resistant to the kind of instrumental revision that had been hoped for since Hipparchos first produced a number. The question had sharpened. The answer would now depend less on which instrument measured the distance and more on which physical framework interpreted what the instruments found. One team had already employed a completely different framework. Their result was waiting, and it pointed in an entirely different direction. Mount Wilson Observatory sits in the San Gabriel Mountains northeast of Los Angeles, at an elevation of roughly 5,700 feet. In 1912, Walter S. Adams used its instruments to catalog the star at the center of this investigation, logging its spectrum and entering it into the growing inventory of nearby stellar objects. For most of the 20th century, Mount Wilson remained among the premier observation sites on Earth. In 2021, a team working with modern instrumentation at that same mountain produced the most favorable age result this paradox had ever generated. The Cara array operates at Mount Wilson. It combines light from 6 individual telescopes distributed across the mountain, with baselines extending to approximately 1,080 feet. By merging light from separated apertures, the array achieves angular resolution far beyond what any single mirror could deliver. At that resolution, it can directly measure the apparent angular diameter of nearby stars as they appear in the sky. That capability matters because it sidesteps one of the central uncertainties in standard isochrone fitting. Conventional age calculations require knowing a star's luminosity, which requires knowing its distance. If the distance carries uncertainty, the luminosity carries it as well. The Cara array measures something different: how wide the star appears in the sky. Combine that angular diameter with a spectroscopically determined surface temperature, and you can calculate the star's physical radius and luminosity directly, without relying entirely on a parallax-derived distance. The 2021 analysis combined this angular diameter measurement with the MESA stellar evolution code and applied Vandenberg's Victoria Regina isochrone suite. The result? 12 plus or minus 0.5 billion years. The upper bound of that range is 12.5 billion years, comfortably below the universe's confirmed age of 13.787 billion years. At 12 billion years, the paradox disappears entirely. A result that cleanly resolves a long-standing problem deserves the same scrutiny it would face if it had deepened the problem. The Cara method depends on the accuracy of the surface temperature measurement, which comes from spectroscopy and is itself model-dependent. The angular diameter, while more directly measured than a parallax-based luminosity, still requires calibration against reference stars. The connection between angular diameter and age still passes through a stellar evolution model, carrying its own embedded assumptions. Raising these points is not a dismissal of the result. 12 billion years is legitimate science from a legitimate methodology. It represents the most direct, independent constraint available for this particular star, and the approach holds real advantages over pure isochrone fitting. But a favorable result and a correct result are different categories, and conflating them repeats the same error that surrounded Bond's 2013 paper. Mount Wilson delivered this star to science in 1912. A century later, instruments at that same site appeared to offer an exit from the paradox. Whether this was the actual exit, or merely the best available one found so far, would become clearer once a completely independent dataset had been applied to the same question. In June 2022, the European Space Agency published Gaia Data Release 3. Contained the most precise parallax measurement available for this star, placing it at approximately 201 light-years. Researchers fed that number into the 2 leading isochrone suites, Parsec and Baste, and ran the full analysis. The result? 13.8 plus or minus 0.5 billion years. Upper bound 14.3. The center of the distribution sitting essentially at the boundary of the universe's confirmed age. Now hold that result beside the Kara result from 2021. 12 plus or minus 0.5 billion years. The two analyses used the same underlying satellite distance. They produced ages separated by 1.8 billion years. To express that spread in concrete terms, the entire age of planet Earth is roughly 4.5 billion years. The disagreement between two methodologically rigorous analyses of the same star spans approximately 40% of Earth's entire existence. Both results were produced by careful teams using legitimate physical frameworks. Both applied the best available data. They arrived at different answers because they embedded different physical assumptions in their models. The Kara approach anchored the analysis to a directly measured stellar diameter, reducing dependence on parallax to luminosity conversions. The parsec and Basti approach relied more heavily on the isochrone grid structure and treated the full photometric and spectroscopic dataset as the primary constraint. The uncertainty in this problem does not chiefly arise from instrument noise. Photon counting errors, detector drift, and atmospheric interference account for a small fraction of the total spread. The uncertainty lives in assumptions physicists embed into theoretical frameworks before any observation is taken. The stellar evolution models are structured approximations of how stars behave, constructed from known physics and calibrated against well-studied reference stars. When a metal-poor halo star billions of years older than most stars in the galaxy is processed through those models, the result is only as reliable as how well the calibrations extend to objects of that character. For this category of ancient metal-depleted stars, the number of comparable, well-characterized objects is sparse. The spread between 12 and 13.8 is not a sign that measurements are failing. It is a sign that the theoretical frameworks used to interpret precise observations have not converged on a single answer. When two frameworks disagree by more than the full width of the paradox being investigated, declaring that paradox resolved requires choosing one framework over the other and asserting that choice is definitive. No one had done that. 13.8 keeps the tension alive. 12 suggests it might dissolve. Which answer is correct depends on physics that current instruments cannot distinguish at the required precision. The star's light carries fixed information about its temperature, brightness, and surface chemistry. What changes between analyses is the mathematical architecture used to convert that light into a count of years. That architecture has never been independently verified against a star of this exact age, mass, and chemical poverty. The gap lives at the leading edge of stellar physics, in territory where the calibrations grow thin. And beneath all of this, a completely separate crisis in cosmology had been quietly intensifying for years, one that threatened to render every calculation in this investigation irrelevant at its foundation. The Hubble constant describes how rapidly the universe is expanding today. Measure it locally by observing nearby galaxies and calibrating the distance ladder through Cepheid variable stars and Type 1a supernovae. Measure it globally by analyzing the cosmic microwave background, the oldest light in the universe. Both methods are mature. Both rest on vast data sets assembled across decades. They disagree. Local measurements using Cepheid variables combined with supernovae produce a Hubble constant near 73 kilometers per second per megaparsec. At 73, the universe is expanding relatively quickly. Running that rate backward through time implies a universe roughly 12.66 billion years old. The Planck cosmic microwave background analysis produces 67.4 kilometers per second per megaparsec. At that rate, the universe expands more slowly. Running that backward implies an older universe consistent with the 13.787 billion year figure anchoring every discussion in this investigation. 67.4 versus 73 is not a rounding error. Expressed statistically, the discrepancy sits at approximately 5 sigma. In probability, 5 sigma means the chance of that gap arising from random measurement noise is less than 1 in 3 million. Physicists treat 5 sigma as the threshold for declaring a confirmed discovery. The Hubble tension clears that threshold, making it exceedingly unlikely to evaporate as measurements are refined further. As of early 2026, the tension remains unresolved. This is confirmed. Wendy Friedman at Carnegie Observatories has been working toward an independent measurement using the James Webb Space Telescope. Her most recent result, using a different calibration approach based on tip-of-the-red giant branch stars, placed the constant near 70.4. That figure sits between the Planck result and the Cepheid-based result. Some researchers interpret the intermediate value as evidence of systematic error on both sides. Others read it as evidence that the tension is genuine, persistent, and indicative of something in the fundamental physics that the standard cosmological model has not yet incorporated. Here is why this matters for the star that opened this entire investigation. If the local measurement is correct and the true Hubble constant runs nearer to 73, the universe's age is approximately 12.6 billion years. At 12.6 billion years, a star with a central age estimate of 14.2 billion years is not a close call. The gap exceeds 1.5 billion years. No published uncertainty range for this star is wide enough to bridge that interval without discarding the underlying measurements. At 12.6 billion years, the paradox is no longer a measurement discrepancy. It becomes a direct conflict between two independently established bodies of physics, each observing reality through a different lens and reaching mutually incompatible conclusions about how old the universe is. The Hubble tension does not merely threaten the age of this star. It threatens the framework within which the star's age has been calculated. If the standard cosmological model breaks at the level of the Hubble constant, then every age derived from that model, including the universe's own, demands fundamental revision. The question of whether this star predates its own universe becomes unanswerable until the universe's age is known with confidence. That 5 sigma uncertainty, still growing, is where the investigation currently stands. Scientists chose to return to fundamentals. If the distance was wrong, correct the distance. If the oxygen was wrong, correct the oxygen, and buried inside the stellar models themselves was another number that had been wrong for decades, one so technically specialized that only nuclear physicists had cause to examine it closely. Inside stars hotter than approximately 20 million degrees Celsius, the dominant energy source is the CNO cycle. Carbon, nitrogen, and oxygen atoms serve as catalysts in a reaction chain where hydrogen fuses indirectly by cycling through those heavier elements repeatedly. The rate-limiting step in the chain, the slowest reaction governing the total pace, involves a proton striking nitrogen-14 and generating oxygen-15. Think of a factory assembly line with one slow station at its center. Every other station can operate at full speed. That one station controls total throughput. For decades, stellar models used a reaction rate for that step measured in the 1980s. That rate was embedded in the code used to calculate how rapidly a star burns through its fuel and fed into age estimates throughout the field. The value circulated unchallenged for nearly 20 years. Physicists at the Luna Underground Laboratory in Italy revisited the measurement. Their particle accelerator was buried beneath a mountain in Gran Sasso, shielded from the cosmic ray background that had introduced noise into earlier surface experiments. Running reactions at energies closer to actual stellar conditions generated a more precise result. The published rate for nitrogen-14 proton capture had been overstated by roughly a factor of 2. This is confirmed. The measurement has been independently reproduced. An overstated rate by a factor of 2 means the CNO bottleneck in real stars runs at roughly half the assumed speed. Half the speed means lower energy output. Lower energy output means the star requires longer to reach its current evolutionary state. Feed the corrected rate into this star's model, and the inferred age shifts. It shifted upward by 0.16 billion years. Upward. The correction made the star appear older. The expectation had been the opposite. Slower reactions in some configurations lower inferred ages by altering how energy propagates through the stellar interior. In this particular star, given its mass, its metal-poor composition, and its position on the subgiant branch, the corrected rate drove the age in the wrong direction. The fix widened the gap rather than closing it. 0.16 billion years is 160 million years. Placed against a paradox already measured in fractions of a billion, that addition counts. The star was already sitting above the universe's measured age. This correction moved it further from safety. What makes this especially difficult is that the correction was legitimate. The Luna measurement is careful, precise, and confirmed. The nuclear physics is sound. An entire generation of scientists operated with one rate while nature was running a different one. When the error was identified and corrected through rigorous laboratory work, the star's inferred age increased rather than decreased. Sound science deepened the problem rather than relieving it. Each layer of this investigation repeats the same pattern. Fix something real, and the paradox endures. The star does not yield, and one more layer remained beneath, one that reached further back than any model to the question of what had to happen before this star could exist at all. The paradox runs on numbers. But the story behind the numbers reaches further than any measurement, further than any telescope, further than the star itself. Every iron atom inside this star carries a story about what came before it was born. Iron is confirmed to be present in the star's spectrum. The concentration is extraordinarily low, roughly 1/250th of the iron level in the Sun. That fraction is not zero, and that is where the argument begins. Iron cannot be made in the Big Bang. The conditions in the immediate aftermath were hot enough to fuse hydrogen and helium and trace amounts of lithium, but nothing heavier. Every iron atom in the universe was forged inside stellar interiors through nuclear burning that occurs only in massive, short-lived stars. When those stars died in supernova explosions, they scattered their contents into surrounding gas. That enriched gas later collapsed into new stars. For this star to contain any iron whatsoever, at least one prior generation of stars had to live a complete life and die violently before this object crystallized. At least one supernova had to seed iron into the gas cloud that would eventually become this star. Those predecessors are called population 3 stars, the first generation. They formed from the pure hydrogen and helium left by the Big Bang, containing no metals at all. Theoretical models predict they were extremely massive, possibly hundreds of times the mass of the Sun, and burned through their fuel in just a few million years before exploding. They have never been directly observed. The James Webb Space Telescope has identified candidate population 3 systems at a redshift of roughly 6.6, placing them around 800 million years after the Big Bang. Candidates only as of early 2026. Candidate status means the spectral signatures are suggestive but unconfirmed. If population 3 stars formed within the first few hundred million years after the Big Bang, consumed their fuel, and exploded, then the gas they enriched had to cool, collapse, and form a second generation before this star could exist. Each step takes time, hundreds of millions of years at minimum. Compress that chain of events. Big Bang. First stars form. First stars explode. Enriched gas disperses. Gas cools. Second generation forms. Each phase erodes the available window. If the universe is 13.787 billion years old, and this star is 14.2 billion years old, there was no window. The entire sequence cannot fit. Even at the formal lower bound of the uncertainty range with the star at 13.8 billion years, the time available for an entire stellar generation to live, produce iron, die in supernova, and enrich the gas that formed this star is compressed to tens of millions of years. No known population 3 scenario completes a full life cycle in that window. The star's own chemistry implies a formation history that barely fits inside the universe's confirmed timeline, and in some configurations does not fit at all. Every object in the sky moves. Stars appear fixed because they are distant, but they travel. Planets orbit, galaxies drift, and this star is moving at roughly 800,000 miles per hour. That velocity is confirmed. Gaia mission data established it with precision. 800,000 miles per hour through the Milky Way's halo, far above the galactic plane, on an orbit that encodes the history of where this object originated. Orbital mechanics preserve information across vast spans of time. A star's current position, velocity, and direction are the cumulative product of every gravitational interaction it has experienced across billions of years. Work backward, through those equations and the path that generated the current velocity points to a specific type of birth environment. This star's orbital dynamics are consistent with formation inside a dwarf galaxy. The Milky Way itself was not its birthplace. A smaller galaxy, gravitationally seized and dismembered by the Milky Way's tidal forces more than 12 billion years ago, is the more plausible origin. The process is galactic cannibalism, confirmed to have occurred repeatedly throughout the Milky Way's history. Dozens of ancient disrupted dwarf galaxies have left trails of stars scattered through the halo. The specific galaxy this star came from has never been identified. The disruption happened before systematic astronomical surveys existed. By the time anyone looked, the galaxy was gone. Its stars had dispersed across the halo, mixing with debris from other mergers, losing the spatial coherence that would allow identification. The Gaia mission has reconstructed the Milky Way's assembly, history in substantial detail, mapping ancient merger events by grouping halo stars with matching orbital properties and chemical signatures. Several disrupted dwarf galaxies have been recovered this way. their identities reconstructed from the kinematic and chemical fingerprints of scattered survivors. The origin galaxy of this star has not appeared in any of those groups. The star's properties place it in the correct age and chemical range, but no coherent stream of similarly moving, similarly composed stars has been traced back to a shared progenitor. The parent galaxy either dispersed too thoroughly or merged too early for Gaia's current data volume to recover it. What survives is the velocity. 800,000 miles per hour is a kinematic fossil. The preserved momentum of a collision that concluded before any human civilization arose. That galaxy's gravity shaped the orbit this star still follows today. Chemical evidence reinforces the picture. The star's iron abundance, 1/250th of the Sun's level, matches populations from extremely early metal-poor environments. The ratios of oxygen, magnesium, and silicon to iron point to a formation environment enriched primarily by core collapse supernovae from massive, short-lived stars. That pattern is consistent with a small galaxy that generated stars rapidly and intensely in the early universe before being absorbed. The origin story is coherent. It is theory supported by consistent orbital and chemical evidence. But without direct identification of the parent galaxy, it remains theory. A galaxy absorbed more than 12 billion years ago, leaving behind no catalog entry, no photometric survey record, nothing but the velocity of one surviving star. Something else was missing too. An error buried inside a correction everyone assumed was complete. Every published age estimate for this star incorporates a correction for helium diffusion. That correction reduced the inferred age by approximately 1 billion years. It was applied because stellar physics confirmed that helium, being heavier than hydrogen, gradually settles toward a star's core over time. Models that ignore this process compute the wrong stellar structure, and from that wrong structure derive a wrong age. The correction is real. The process is confirmed. What the literature did not address clearly until relatively recently is that the correction itself carries an error. Helium diffuses through the stellar interior at a rate depending on local temperature, density, and composition across every layer simultaneously. Calculating that rate from first principles requires knowing those interior conditions precisely. Astronomers do not have that information directly. They infer interior conditions from surface observations and theoretical models, use those inferred conditions to calculate the diffusion rate, then apply the diffusion correction to the same models that generated the inferred conditions in the first place. The calculation is built on its own output. The diffusion rate in current stellar models is an approximation. This is acknowledged in the published literature. Multiple research groups have noted it as a source of systematic uncertainty. No adequate observational constraint exists to pin down the actual diffusion rate for a metal-poor subgiant branch star of this type. Observations of surface helium abundances in white dwarfs have been used to calibrate diffusion in those end states. But that calibration does not transfer cleanly to an actively evolving subgent. The rate at which helium is sinking through this star's interior right now is unknown. The magnitude of the error that approximation introduces is also unknown. A known error can be corrected. An error whose magnitude has never been measured cannot be subtracted. It propagates invisibly through every published result. Every age estimate produced for this star, from the earliest measurements through the 2025 TESS result, carries this unquantified term. Published. Uncertainties do not include it. They account for statistical scatter in observations, formal distance uncertainties, and stated composition uncertainties. They do not include an unknown systematic from a diffusion model whose accuracy has never been adequately tested for stars of this category. When a paper reports 14.2 plus or minus 0.4 billion years, that plus or minus 0.4 is not the complete uncertainty. It is the formally calculable portion. The true uncertainty is larger. By how much, nobody currently knows. Science applied a correction it believed would eliminate a systematic bias. The correction was real and necessary. The method used to apply it carries its own unresolved imprecision. The error bars in every published result are, by some unquantified degree, too small. This is among the quieter findings in the investigation, and potentially one of the most consequential. Every age ever published for this star rests on a helium diffusion model that has not been fully validated for stars of this class. That model underlies every number, every stated uncertainty, every graph in every paper. The gap between what it assumes and what is actually happening inside the star has never been measured. The picture was growing harder to read, with more corrections applied and more unquantified residuals accumulating. The next approach tried something entirely different. 45,000 light-years above the plane of the Milky Way, visible from the northern hemisphere as a faint smudge in the constellation Hercules, sits a globular cluster called M92. It contains more than 300,000 stars. Its age has been measured at approximately 14.2 billion years. That figure is independently confirmed by multiple research teams using different stellar evolution model suites. The measurements do not all agree exactly. They cluster around 14.2 billion years with enough consistency that the value stands as one of the most robustly established ages in observational astronomy. The cluster sits roughly 26,000 light-years from Earth. Astronomers date it by identifying the turn-off point on its color magnitude diagram, the luminosity at which the most massive surviving stars begin leaving the main sequence. That turn-off luminosity is a function of age. Different teams, different codes, different assumptions, all converging near the same number. The 2025 TESS asteroseismology campaign produced an age for this star of 14.2 billion years, the same figure. Two independent objects. One, a cluster of 300,000 stars measured through population-level photometry. One, a single nearby star measured by listening to acoustic waves propagating through its interior. Different objects at vastly different distances, different methodologies, different research teams. The same answer. Convergence like this is not automatic, it carries weight. When two completely different measurement approaches, one classical photometry applied to a distant cluster and one acoustic wave analysis applied to a nearby single star return identical results, the coincidence demands explanation. One interpretation is that stellar physics is internally consistent. The models describing how stars evolve and age are capturing real physics. When two entirely separate measurements of two entirely separate objects produce matching results through independent methods, confidence in the underlying framework rises. The other interpretation carries less comfort. If the stellar evolution models carry systematic biases, both measurements could agree while both being wrong. The same theoretical assumptions used to date globular clusters are embedded in the methods used to date individual stars. A shared error in those assumptions would push both M92 and this star toward the same incorrect conclusion by the same incorrect pathway. One additional complication: the Hubble tension has not been resolved. If the locally measured expansion rate is correct, the universe is approximately 12.66 billion years old. That age, both M92 at 14.2 billion years and this star at 14.2 billion years, would be impossible objects. Two confirmed objects measured by independent methods, both returning ages that exceed the universe's timeline. Either stellar physics is accurate and the universe's standard age is wrong, or the universe's age is accurate and stellar physics harbors a systematic error large enough to shift both measurements by more than 1 billion years. Both possibilities are active. The convergence between M92 and this star does not confirm that stellar physics is reliable. It confirms that stellar physics is internally consistent. Those are different statements. Resolving which one applies required a new kind of measurement, one that no one had believed would work on a star like this. In 2018, a NASA satellite launched primarily to detect planets orbiting distant stars began an observational campaign that no one initially expected to yield results of this magnitude. The Transiting Exoplanet Survey Satellite, TESS, was engineered to find planets by detecting the faint dimming of starlight when a planet passes in front of its host. To accomplish this, the satellite monitored stars continuously for weeks at a time, tracking brightness with extreme precision. That same precision proved applicable to something entirely different. Brightness fluctuations from planetary transits last hours. The oscillations produced by acoustic waves moving through a stellar interior are faster, subtler, and far richer in information about the star itself. Stars breathe. That is the simplest way to describe it. Sound waves generated in the turbulent outer convective zone travel inward through the interior, reflect off internal structural boundaries, and return to the surface, generating faint rhythmic brightness oscillations. Those oscillations encode information about the star's internal density profile, its mass, its radius, and ultimately its age. The field that interprets this information is called astroseismology. The analogy is a medical ultrasound using reflected sound to image the body's interior, except the body is a star, and the echoes complete a cycle roughly every 27 minutes. For a star this ancient and chemically unusual, detecting those oscillations from space had been considered marginal. The signal was expected to hover at the edge of what even a high-precision photometric satellite could resolve. In Sector 51 of its observing schedule, TESS collected light from this star in 2-minute cadence mode, its highest available time resolution. The resulting data revealed oscillations, faint but real and measurable with confidence. The primary oscillation frequency, called NU max, registered at 611.3 microhertz. That is the highest nu max ever recorded for a metal-poor star. The object was pulsing almost imperceptibly, and the satellite detected it. Researchers extracted physical parameters using mathematical relationships called scaling relations. The derived mass, 0.75 times the mass of the Sun. The derived radius, 2.078 times its radius. From those values combined with the star's luminosity and chemical composition, an age emerged. 14.2 billion years, plus or minus 0.4 billion years. This result carries a different character than all previous estimates. Asteroseismology is entirely independent of the distance and isochrone chain that produced earlier ages. It does not rely on Hipparcos parallax or even the Gaia successor. It does not place the star on a color magnitude diagram. It listens to the star's own interior oscillations and extracts structure from the physics of sound. The central value still sits above the universe's confirmed age of 13.787 billion years. The formal lower bound of 13.8 billion years lands exactly at the boundary. Every improved technique, every correction, every new instrument has failed to place this star unambiguously inside the universe's timeline. And there was a problem with the technique that researchers identified while reporting the result. The 2025 astroseismology result was the most precise physical measurement ever made of this star's interior. It was also built on a mathematical framework calibrated for an entirely different kind of star. Asteroseismology scaling relations, the equations converting oscillation frequencies into stellar mass, radius, and surface gravity, were developed using stars with near-solar chemical compositions. The Sun and hundreds of similar stars provided the calibration sample. Researchers refined the relations until the equations returned accurate physical parameters for solar-type stars. The calibration was rigorous and took years to construct. Metal-poor stars were not included. The logic behind that exclusion was practical and at the time reasonable. Oscillations in metal-poor stars were expected to be too faint for reliable detection, and their extreme chemical compositions would place them outside the valid domain of equations calibrated on solar chemistry. Lower metallicity alters how energy moves through a star's outer layers, shifting the frequencies and amplitudes of oscillations in ways the solar-calibrated relations were not designed to handle. For most of asteroseismology's history, metal-poor stars simply were not being measured. The TESS campaign invalidated that assumption. The oscillations were detectable. The technique worked on this star, producing a clean new max signal and extractable parameters. The field had been unnecessarily conservative for decades. In demonstrating the technique worked, the researchers uncovered the calibration problem. When the standard scaling relations were applied to this metal-poor star, and the results were cross-checked against independent observational constraints, the standard relations underpredicted NU max by 14%. 14% is not a rounding error. It is a systematic offset embedded in the mathematical framework used to interpret the entire measurement. A 14% error in nu max does not stay at nu max. The scaling relations chain outward from frequency to surface gravity, from surface gravity to mass, from mass to radius, and from radius to luminosity. Each calculation depends on the one before it. An offset, introduced at the NU max stage, propagates through every derived quantity. The mass shifts. The radius shifts. The age calculated from those parameters shifts by an amount that has not been quantified because the correction has not yet been applied. Researchers documented the miscalibration. Fixing it requires assembling a calibration sample of metal-poor stars measured at high precision, which demands observations that do not yet exist. As of early 2026, the scaling relations used to produce the 14.2 billion year result still carry the uncorrected 14% offset. The formal uncertainty of plus or minus 0.4 billion years captures statistical scatter in the oscillation measurements and some modeling variation. It does not capture the effect of the 14% nu underscore max under prediction, because that effect has not been calculated. The most precise measurement ever made of this star's age is simultaneously the measurement with the best characterized known flaw. Demonstrating the technique's applicability to metal-poor stars was a genuine advance. It also exposed exactly what is wrong with the technique as currently implemented. The investigation has reached the best available answer. That answer is known to carry an uncorrected error, sits at the boundary of the universe's timeline, and has not been independently confirmed. Here is where things stand as of early 2026. An error budget, not a verdict. The best current estimate of this star's age is 14.2 billion years, plus or minus 0.4 billion years, from the 2025 TESS asterosismology campaign. That result has not been independently replicated by a separate team using a separate instrument. The formal lower bound is 13.8 billion years. The Planck missions. Measurement of the universe's age is 13.787 billion years. The gap between the star's formal lower bound and the universe's confirmed age is 13 million years. On a cosmological scale, that margin barely registers. Now consider what is not captured in the plus or minus 0.4. First, the asterosismic scaling relations underpredict NU max by 14% for metal-poor stars of this type. The correction has not been applied. The direction and magnitude of its effect on the derived age remain unknown until recalibration is complete. Second, the oxygen abundance is contested between research groups with a separation of 0.15 dex between competing measurements. That disagreement translates to a possible swing of roughly 0.7 billion years in the inferred age. Third, the helium diffusion model applied to all published ages, including this one, carries an approximation error whose magnitude has never been quantified. Every published error bar omits that term. Fourth, the Hubble tension. If the locally measured expansion rate is correct, the universe is roughly 12.6 billion years old. At that age, the star exceeds the universe's timeline by 1.6 billion years, well outside any published uncertainty range. Each of those four terms could, resolved in the wrong direction, push the star's true age above any published estimate. Some could push it lower. The honest position is that no one currently knows, because the required corrections have not been completed. The investigation has not failed. It has produced increasingly precise measurements and an increasingly precise map of where residual uncertainties live. That process is how scientific knowledge advances, by cataloging what is established and being explicit about what is not. The formal age estimate, narrowed from a range of 12 to 16 billion years in the late 1990s, to a single value of 14.2 plus or minus 0.4 billion years by 2025. That is genuine progress. What it has not produced is a measurement that unambiguously places this star inside the universe's timeline. The best available result sits at the boundary, carried by error bars that are formally too small, built on a technique with a documented 14% miscalibration, sensitive to a contested oxygen measurement, and resting on an unquantified diffusion term. The universe may be younger than the star. The models may carry errors that make the star appear older than it truly is. Both remain genuinely open. The investigation has a best answer. The best answer has documented limits. And the history of every previous best answer for this star is a record of those limits being found, examined, and in some cases exceeded. In 1997, the first modern age estimates placed this star between 14 and 16 billion years. The universe's measured age at that time ranged between 12 and 14 billion years, depending on which Hubble constant measurement was trusted. The ranges overlapped just enough to avoid direct contradiction. Some researchers expected the paradox to dissolve as measurements improved. Measurements improved. The paradox did not dissolve. By the early 2000s, Hipparcos parallax data placed the star closer than expected, pulling the inferred age downward toward 12 to 14 billion years. Several papers declared the problem resolved. Then, Gaia data revealed the Hipparcos distance carried a small but consequential error. The corrected distance moved the age back up. Early stellar models excluded helium diffusion. Incorporating it dropped the age by approximately 1 billion years. That appeared to be resolution. Then, the diffusion rate itself was identified as an approximation carrying an unquantified error, and every subsequent paper inherited that error without accounting for it. The oxygen abundance came into focus as a major source of uncertainty. Measuring oxygen in an ancient metal-poor star requires spectral analysis methods that different groups apply differently, and the competing values diverge by 0.15 dex, carrying a 0.7 billion year swing in inferred age. The disagreement has not been settled. The CNO nuclear reaction rate was corrected downward by a factor of 2 through careful underground laboratory work. The correction was real and verified. The inferred age moved upward by 0.16 billion years. Asterosi-ismic scaling relations turned out to carry a 14% systematic offset for metal-poor stars. The 2025 result applied the technique for the first time, produced the most precise age measurement yet, and revealed the calibration gap in the same publication. The full span of published age estimates from 1997 to 2025 covers 12 to 16 billion years. That range does not represent random noise converging on a true value. It represents systematic errors, each concealed behind the previous framework, each exposed only when the field developed tools capable of probing deeper. Every correction resolved one uncertainty and revealed another. Every new instrument brought the investigation closer to the star's true age and confirmed that the true age remains near the boundary of cosmological possibility. Best estimates now cluster between 13.8 and 14.2 billion years. They have not converged to a single value. The spread within that cluster reflects genuine unresolved physics, not careless measurement. The cosmological context remains in motion around that cluster. The Hubble tension has not been resolved. If the locally measured expansion rate is correct and the universe is roughly 12.66 billion years old, every estimate in that cluster is impossible. The paradox transforms from a rounding problem into a fundamental conflict between two independently established bodies of physics. 28 years of improving measurements have not resolved the question. The tools have grown sharper. The models have grown more detailed. The systematics have been cataloged with increasing precision. The central question, whether this star is older than the universe it inhabits, remains open. The star is still there in Libra, roughly 190 light-years from Earth, traveling at approximately 800,000 miles per hour through the Milky Way's halo. It continues its orbit, following a path it has traced for longer than any current instrument can determine with certainty. That path leads back to a galaxy that no longer exists, absorbed by the Milky Way more than 12 billion years ago, its identity unrecorded in any catalog. The Hubble tension remains unresolved as of early 2026. Two measurement methods for the universe's expansion rate disagree by 5 sigma, and neither has yielded. The disagreement is not a footnote rounding error. It is a direct conflict between the two most precisely measured quantities in modern cosmology, and its resolution will reframe how every stellar age estimate is interpreted. The oxygen abundance in this star remains contested between research groups. The asteroseismic scaling relations for metal-poor stars carry a 14% miscalibration that has been documented and not yet corrected. The 2025 result, the most precise age measurement ever produced for this object, has not been independently replicated. The helium diffusion model applied across all published ages carries an unquantified systematic error that flows through every number in the literature. Population 3 stars, the generation that had to live and die before this star could form, have never been directly confirmed. The James Webb Space Telescope candidates at redshift 6.6 remain candidates only. The physics of the earliest stellar generation is inferred rather than observed. The origin galaxy of this star, disrupted and absorbed by the Milky Way more than 12 billion years ago, has not been matched to any known merger event in Gaia's reconstruction of the Milky Way's assembly history. It existed. It is gone. Its surviving record is the velocity of one star. The question of whether a single observed star can compel a revision of the universe's measured age depends on which universe age is correct, which stellar evolution model is applied, which oscillation scaling relation is used, and whether every physics process inside the star has been accurately captured by models built on approximations. Changing any one of those inputs can shift the conclusion. As of early 2026, none of them has been pinned down with sufficient precision to close the case. The extremely large telescope is under construction in the Atacama Desert in Chile. When its mirror is complete, it will resolve stellar spectra at precision that current ground-based instruments cannot reach, potentially settling the oxygen abundance dispute. The Nancy Grace Roman Space Telescope, targeting launch in the late 2020s, will generate asteroseismic data for thousands of metal-poor stars, and finally construct the calibration sample needed to correct the scaling relation error. Next-generation space-based observatories now in design will constrain the Hubble constant through multiple independent methods simultaneously. Those instruments will produce new answers. Some of those answers will shift the numbers in this investigation. Some will shrink uncertainties. At least one will likely reframe the question in a way that no one has yet anticipated. The star holds its orbit through the halo. The instruments are pointed at the sky. And somewhere between those two facts, between the ancient light still traveling and the lenses we are building to receive it, the answer continues to wait. What makes this investigation different from most problems in science is that it is not simply a measurement waiting to be refined. It is a collision between two of the most reliable things physics knows how to do: count how old a star is and count how old the universe is. Both methods are mature. Both have been cross-checked against independent approaches repeatedly. Both produce results that, as of today, have not been fully reconciled. That is not a failure of science. That is what science looks like when it reaches the edge of what current tools can resolve. The star existed before any instrument was built to observe it. It was burning before the sun formed, before the earth existed, before any molecule capable of thought had assembled anywhere in the cosmos. Whatever age it truly is, that age is written into its interior in a language of nuclear physics and acoustic oscillation that we are only now beginning to learn to read precisely enough for the question to matter. The answer, when it arrives, will not merely close a file on one unusual halo star. It will either confirm that our picture of cosmic time is accurate to within a hair, or it will force a revision of that picture at a level that reshapes what we think we know about the first billion years of everything. Either outcome is worth pursuing. The star is still burning. The telescopes are still building, and the investigation is not finished.